Hey everyone, welcome to Unit 3, Lecture 4 in UChem 42U, Chem 1111. We're continuing on with thermodynamics, and the first page here I have is from your appendix. Well, maybe not your personal appendix, but the appendix at the end of the book. Appendix D, Standard Thermodynamic Functions. We're going to look a lot at delta H naught F, the standard heat of formation, the standard molar enthalpy change. Little f stands for formation. The little naught there means 1 bar of pressure and usually 298.15 Kelvin. That is known as the standard state. So aluminum, its standard state is a solid. So at 25 degrees Celsius or 298.15 Kelvin, and essentially room pressure, aluminum is a solid, right? Calcium is a solid, argon's a gas. So we see the values for the delta H naught formation. Now the delta G naught and S naught, those are going to be learned months from now, but they are helpful things as well. So let me go to the mini chapter text thingy. Enthalpies of formation. This is page 145. So how do we get those energy and enthalpy changes? We could keep performing, there we go, Unit 3, Lecture 4, experiments, but that will be insurmountable. There's a heck of a lot of chemical reactions. Using the first law of thermodynamics and the idea of a state function, we can calculate enthalpy changes for almost any reaction using experimental values. The formation reactions. To make use of formation, we must also understand the concept of a standard state. I started the lecture today with that. The simply is the form that is most stable under specified conditions. Normally these are 1 bar. In my olden days, instead of bar, I would say atmosphere. A bar and an atmosphere are pretty close to each other in value. And sometimes I'll still say atmosphere, even though it's, like I said, slightly different than a bar. 298 Kelvin and a concentration of 1 molar if the substance is in solution. Bromine is most stable as Br2, right, diatomic molecule. Remember Hofbrinkel, the clown? Br2, not Br, and it says a liquid, not a gas or a solid. Most metals are solids in their standard states. Oxygen, nitrogen are gases in their standard states. So O2, N2 gas, and O2 gas are the standard states of those elemental molecules. A formation reaction will have just a single product with a stoichiometric coefficient of 1. And all the starting materials are elements or elemental molecules in their standard state. So to create a heat of formation reaction, which is an important thing to do, those are rules and enthalpies of reactions involving gases vary with pressure. So that's why we have to talk about a specified pressure and vary with concentration. So that's why we have to talk about concentrations. A formation reaction produces 1 mole of chemical substances from the elements or elemental molecules that constitute the product with those elements in the standard states. The product doesn't have to be in the standard states, but the elements or elemental molecules on the left-hand side of the equation do have to be in their standard states. When the partial pressure of each gaseous reagent or reactant, same thing, is 1 bar and the concentrations of each species is 1 molar, we're talking about liquids, solutions, the enthalpy change is in a formation reaction is the standard enthalpy of formation. And again, it's called delta H naught F. The naught is like a circle of 0. In Britain, instead of tic-tac-toe, the game's called noughts and crosses. Okay, so it's called a knot, N-A-U-G-H-T, not a knot, N-O-T, or a knot, K-N-O-T. That was a lot of knots. I twisted myself up in knots, didn't I? Delta H naught F. Reaction enthalpies may also vary with temperature, but most tabulations are at 298 Kelvin. So we'll assume that temperature unless you're told something else. So here's some examples of some formation reactions. Oh, here's a picture of forming iron, Roman numeral 2 oxide, ferric oxide in the olden days. It's exothermic, so you're forming 1 mole of FeO solid from a mole of Fe and half a mole of oxygen. Br2 liquid goes to Br2 gas, so that is endothermic, 30.9 kilojoules per mole. That's an endothermic reaction. half N2 plus half O2 goes to NO gas. So 1 mole of NO is formed by half a mole of N2 and a half a mole of O2. CH3OH, methanol, 1 mole of methanol. That's from graphite, hydrogen, and oxygen. And that's exothermic. Delta H is minus 239.2 kilojoules per mole. Carbon graphite going to carbon graphite. Now that one's 0 because you've got the same thing on both sides. So that last one isn't a formation reaction, okay? Because you aren't forming anything new from what you started with. Notice how you're allowed to put halves in front. You may have been taught in some older classes or seen videos where people say, oh, don't use halves for a coefficient because kids will think it's half a molecule. No, we're talking about moles. You can have half a mole of something just like you can have half a dozen bagel, right? Okay, now I'm hungry. Then there are the formation reactions can be exothermic or endothermic. The majority, if you look in the table, seem to be exothermic. If you have an element in a state that's different from the standard state, it has a positive standard formation enthalpy. For example, Br2 gas, it is positive 30.9, so it's not in the standard state, so its delta H naught F is positive. Fractional coefficients are allowed. And if the element's already in a standard state and the product is the same as the element, delta H naught of F is 0. So delta H naught of formation is 0 for elements or elemental molecules in their standard states. An elemental molecule, if you don't know what that is, that's like O2 is an elemental molecule. It's still a molecule. It's not O by itself, but there's no other kinds of atoms in it. So O2 is an elemental molecule, and in its standard state, the delta H naught of formation is 0. Some reactions, formation reactions, such as oxidation of metals, proceed easy and directly. Others don't. Like methanol, that can't all happen by one step. It happens in a series of steps, and however, once you measure the value, that's what it is, and it's a well-defined quantity. We have Appendix D, which I started the class at, which lists lots of values. You may, if you have a chance, photocopy Appendix D because you're going to need it in a few chapters. So having it nearby, maybe having Appendix D and a periodic table and a table of molar masses all in the same little booklet would help you more efficiently go through questions as we go through things. Okay? Now, having a standard enthalpy of formation, that's useful because it can be used to calculate the enthalpy change for any reaction, any kind of reaction, not just a formation reaction. As an example, consider this reaction here. 2NO2 goes to N2O4. This is not a heat of formation reaction, right? Because even though I just have 1 mole of product on the right-hand side, I got compounds on the left-hand side, not individual elements or elemental molecules. But I can still get the delta H naught for the reaction. And what you do is you take 1 times the delta H naught of formation of the N2O4 minus 2 times the delta H naught of formation of the NO2. That is the short way known as Hess's law, the shortcut of Hess's law. The book makes a big deal of getting into all this nonsense here. And that's not nonsense, but just let me jump straight to the task at hand. Here is what's called Hess's law. If we know the heats of formation, so delta H naught of reaction is the sum. Now this little nu here is going to be the stoichiometric coefficient. So you add up the products of each stoichiometric coefficient times its heat of formation for the product side, plus the next one, plus the next one, plus however many there are, minus the stoichiometric coefficient of each reactant times the delta H naught of formation of each reactant. Okay? And that is what Hess's law is. So in this example here, I would get from Appendix D that the N2O4 is 11.1 kilojoules per mole. So there's 1 mole of N2O4 times 11.1 kilojoules per mole. So you get 11.1 kilojoules. And then the right-hand side was 2 times the delta H naught of formation of NO2. So 2 times 33.2. So 11.1 minus 66 something, minus 55.3 kilojoules. So this reaction is exothermic. During the reaction, a chemical bond forms, but none of the bonds break. So that's what happened. Let's go back. What is my reaction? 2NO2 goes to N2O4. Right. So we're getting more energetically happy, so my delta H naught is negative. Okay. So that minus 55.3 kilojoules was forming 2 moles of NO2. No, was associated with 2 moles of NO2 reacting to form 1 mole of N2O4. If I wanted 1 mole of NO2 reacting, it would be half as much. You can generalize this calculation to find the molar enthalpy for any reagent divided by the appropriate coefficient. And that'll give you a value for a reagent. Okay, let's try another example here. I do call this the shortcut Hess's law because we're going to do an example or two, which is the full Hess's law, which isn't listed in this book, but there are some assignment questions that pop up from time to time. But I'll get to that in a few minutes. Here we have methane. It's CH4 gas plus 2 O2 gas goes to CO2 gas plus 2 H2O liquid. Okay, obviously this reaction has to be balanced. If it's not balanced, it's not good for anything. So the delta H naught reaction is the heat of formation. That's the quick way of saying standard molar enthalpy of formation. So the heat of formation of CO2 gas plus 2 times the heat of formation of H2O liquid, so that's the product side, minus the sum of the heat of formation of CH4 gas plus 2 times the heat of formation, that should say delta H naught F, of O2 gas. The value for O2 is 0, right? 0. So 1 times minus 393.5, you get that from CO2, plus 2 times minus 285.8, you get that for liquid water. Now let me just show you something because kids get tripped up on this. Where's my appendix? There it is. And I'm going to scroll down here and I guess I should look for hydrogen, right? Where are you, hydrogen? There it is. Notice that you have the delta H naught of formation for both liquid and gas, right? Gas being higher than liquid, right? Minus 241.8 is higher than minus 285.83. So be careful when you're looking at tables that you're using the right phase. In this example here, we're using H2O liquid. Okay. Let's now go back to there we go. So, minus on the left-hand side, you got 1 mole of CH4, so that's minus 74.81 plus 2 times 0. So, this combustion reaction, you punch it out and you get minus 890.3 kilojoules. Okay? Standard formation enthalpies refer to 1 bar, 1 molar, and 298. What if a reaction occurs under other conditions? Well, things can change, but delta H depends on those variables too. And the delta H are going to be standard. Okay, hold it. I got it now. Pause for a second.
Call from 20481.
Hello? Okay, I'm back. I'm not sure what that was all about. Someone calling me, offering me free chocolate bars or something. So anyways, under non-standard conditions, that's a bit more complicated, but delta H, the differences aren't going to be that big, even when we depart somewhat from 298 Kelvin, 1 bar, and 1 molar. So that'll be good enough. Just for example, if you're at a slightly different case. So here in example 3.9, we have nitric acid, which is HNO3. There it is. It's produced in the gas phase at elevated temperature and pressure. Important chemical in the fertilizer industry because it can be converted into ammonium nitrate. Following overall chemical equation summarizes the industrial reaction. And if you're following along at home, this is on page 149. Okay. So we got 12 moles of ammonia will react with 21 moles of O2, the gas phase, to give you 8 moles of ammonia plus 4 moles of NO plus 14 H2O. Determine whether this overall process is exothermic or endothermic and estimate the energy change per mole of HNO3. So we're going to do 8 times the heat of formation of HNO3 plus 4 times the heat of formation of NO plus 14 times the heat of formation of H2O. We're going to add all of those together and then subtract the sum of 12 times the heat of formation of NH3 plus 21 times the heat of formation of O2. We're going to do that calculation, get a value, and then divide by 8. Okay? So let's go through here. And 8 plus 4 plus 14 minus 12 plus 21 is minus 3.5 by 10 to the 3 kilojoules, or minus 3540 kilojoules. And this is exothermic. Important to pay attention to the signs. Okay. And then you got to divide by 8 because they wanted it per mole of nitric acid. What's this thing on the right here? The enthalpy of formation depends on its phase because heat is required to melt a ball of substance, right? Okay, we've talked about that before. Liquid to gas, difference is enthalpy of vaporization of water. So you got to keep track of your coefficients. You got to keep track of your phases. Okay, practice exercise 3.9. Determine the energy change per mole of NH3. So you would take 4 times the heat of formation of NO2 plus 6 times the heat of formation of H2O, but this time liquid, minus the sum of 4 times the heat of formation of NH3 plus 7 times the heat of formation of O2. And they want it per mole of NH3. So once you get an answer, then you divide by 4. So it gives you per mole of NH3. If you want the answer, sometimes I write those in on the side here so I don't look all the time. I have to flip through pages. Turns out to be exothermic, minus 349 kilojoules per mole. Okay. Here's an interesting question, example 310, where you have to find the enthalpy of formation of something that may not be in a table. On a test, you might not be given all of Appendix D. You might just be given little snippets to help you with the questions. So maybe octane isn't listed, and you are given a reaction enthalpy. Here it's a combustion reaction of octane, and it's minus 5.5 by 10 to the 3. Use tabulated standard enthalpies to determine the standard enthalpy of formation of octane. Okay, so start with a balanced equation showing combustion of 1 mole of octane. Why not? Because that's going to make things easier as we go through all this. So combustion is given as minus 5.5 by 10 to the 3, right? Minus 5.5 by 10 to the 3 kilojoules per mole. So it's 8 times heat of formation of CO2 gas plus 9 times heat of formation of H2O liquid minus delta H naught of formation of octane. Well, that should say plus 25 over 2, right? It doesn't really matter that part because it's going to be 0 because the heat of formation of oxygen is 0. So I'm going to isolate. So delta H naught of formation of octane is going to be 8 times heat of formation of CO2 plus 9 times heat of formation of H2O minus the heat of combustion. Again, this part here is 0. Plug in the values. Enthalpy of combustion was given in experimental values from the Appendix D, and you get minus 220. So octane is somewhat more stable than the elements from which it forms. Okay, so, and you can try practice exercise 3.10 on your own. And if you do that, you'll be getting pretty good at this. Now remember, before we could estimate the energies of chemical reactions from bond energies, and those look sort of the same, right? Summing something up minus the sum of something else. Both are consequences of Hess's law. For equation 312, match a process in which reactants decompose, and then we combine to get products. In equation 3.5, we look at reactants breaking down, and then we combine to get products. So that's what gives you some similar ideas. If you have a choice, use equation 312, the Hess's law with the delta H naught F, because they're using experimental data, whereas the tabulated bond energies are average. Okay? Estimates. But there are times when it's helpful just to get like a back of the envelope calculation, just to use the bond energies. Section exercise 3.51, 3.52, 3.53. You should try those ones on your own. And of course, email me any questions you might have about it. Now, I want to do something new here that's not in the textbook, which is, I call it the, not full house, but the full Hess. Hess's law, if you've given all sorts of equations, and I'll show you how that works. So I'm going to go to Paint and my canvas here, and I'm going to show you what I mean. Let's say I had a target equation, which was, so this I call full Hess. The target equation, I like to put a little star with a circle around it. This is the desired equation. It's carbon. Now there's all sorts of forms of carbon. The thermodynamically most stable form is graphite. So CgR, I'm going to have 3 of them, plus 4 hydrogen gas, and that's going to form C3H8 gas. Okay, so this is my desired equation, and I want to get delta H naught. And let's say I don't know what the C3H8 delta H naught of formation is. If I do, well then I just look at it off a graph. So suppose I have the following information. I got 3 equations. Equation 1, equation 2, and equation 3. And one has C3H8 gas plus 5 O2 gas goes to 3 CO2 gas plus 4 H2O liquid. And delta H naught 1 is minus 2219.9 kilojoules. Okay, so you're given that equation. Then you would got one here, carbon graphite plus O2 gas goes to form CO2 gas, and delta H naught 2 is minus 393.5 kilojoules. And then a third one, H2 gas plus half O2 gas goes to form H2O liquid, and delta H naught 3 equals minus 285.8 kilojoules. Okay, so I have these 3, and we want to produce C3H8 1 mole. So you got these 3 equations. These 2 are heats of formation equations. The first one isn't, however, it's a combustion. So here's the game we play for full Hess's law. I could say, given the 3 equations, calculate delta H naught and show your work, how you do it. So this is what we do. We start off, we see here, I started the product side. I got a C3H8 on the product side. And then scan. Where do I see C3H8 in any of the reactions? Oh, I see it in reaction 1. It's on the reactant side. And in the full Hess, it's on the product side. So I'm going to reverse equation 1 and make that equation 4. and write it then as 3CO2. I'm going to leave off the phases to simplify things. 3CO2 plus 4H2O goes to C3H8 plus 5O2. And when you reverse an equation that we looked at earlier in this chapter, so this is delta H naught 4, it becomes positive 2219.9 kilojoules. So you switch the sign when you reverse the equation. So REV, reverse equation 1. Okay, now I'm looking and I see a coefficient of 3 in front of the carbon graphite. I'm looking through here. Oh, I only got one carbon graphite in equation 2, but it's just got a 1 in front of it. So I have to multiply every coefficient in equation 3 by 2, and that'll give me equation 5. I said it the wrong way. Every coefficient in equation 2 by 3. That's what I have to do. So I'm going to end up with 3 carbon graphites plus 3O2 goes to 3CO2, and delta H naught 5 would be 3 times minus 393.5. 3 times 393.5 negative minus 1180.5 kilojoules. Okay, and then the other one, I got 4H2, so I'm going to do 4 times equation 3. That's going to be equation 6. So I'm going to get 4H2 plus 2O2 goes to 4H2O. And delta H naught 6 equals 4 times 285.8 minus 1143.2. Okay, so now I'm going to add these equations together. Watch this. I'm going to use a different color. Oh, can I get to a different color? Fill color. Alright, watch this. I'm not going to use a different color. So I'm going to look, what can I cancel out? I have a CO2 gas, 3 of them on the left and 3 of them on the right. So that cancels out. I got a 5O2 on the right. I got a 3O2 and a 2O2 on the left. So they add up to 5O2 on the left. So they cancel the 5O2 on the right. The 4H2Os cancel. 4 on the left, 4 on the right. So I get 3 carbon graphite plus 4H2 goes to C3H8. So I have manipulated as much or little as needed to get the target equation from the given equations 1, 2, and 3. And to get the answer, I just add up the delta H naught 4, delta H naught 5, and delta H naught 6. So 2219.9 plus 1180.5 negative plus 1143.2 negative is minus 103.8 kilojoules, which becomes minus 104 kilojoules. And that is how you use a full Hess's law question. That's a lot of work, I know, but that's what you sometimes have to do. How many times you'll have to do it? I don't know. On a test, maybe once, because it takes a while to do it. Let me just make one up just to show you. Let's do file new. Here, it's always dangerous what I'm going to try here. But let's say I got 2A plus 3B goes to 4C. Okay, and let's say I have an equation A plus B goes to C, and A plus 2B goes to 3C. And this first equation, delta H naught of the reaction is 20, second one is minus 10. So to get the overall equation, you have these two given ones, and there's the delta H naught for these reactions. They may be formation, they may not, but these are these two reactions. So I look and I say, oh, look how easy this one is. I just add 1 and 2 together. I don't have to do any manipulations. So I get 2A plus 3B goes to form 4C, which is what I wanted. And my delta H reaction is to do 20 plus negative 10, and I get 10. Okay? If you go on Khan Academy or Brightstorm, that's a nice site, or even my old friend Tyler DeWitt, you will see worked out examples of Hess's law. Again, the textbook that we have doesn't think they're that big a deal, and so don't do them much, but I think it's good to at least do 1 or 2 as we did there. Okay? So now, let's take a quick look at our PowerPoints. We haven't looked at them lately. Okay, this is all from previous stuff. Now is stuff we're doing now. Non-standard conditions, right. Okay, so it didn't really add anything else. Section 3.6, energy sources, that we can omit. We won't deal with that in this chapter, so don't worry about energy sources. Though we should all be worried about energy sources, right? Okay, let's go back to the mini text here, chapter 3. So again, we're going to omit energy sources. And so let's scroll down here, and hopefully we have enough energy to get through this. This is a Canadian book, so they have to use the word Canada every now and then. Oh, there's some wind turbines for you. And future resources. I hope we find good ways to keep everything going in an environmentally friendly way. And that is a lot easier said than done. Maybe some of you will be the ones who will figure those out. So then, this is a nice thing. Every chapter in this course has a visual summary with pictures and flowcharts for you who are that kind of learner can do that. And the equations are there. Some of you like taking an index card and summarizing the equation on an index card. And there's flowcharts, all sorts of wonderful things to help you get through things, key concepts, objectives. Then we have some exercises, and the odd number ones are in your solution manual, part of your Wiley Plus package of good stuff. Just wondered if they did any full Hess's law. No, they really don't, do they? Okay. Often near the end of each chapter, there's additional paired problems, which are a bit more extra practice, which is good to have more extra practice. And then there's even some more additional problems are often a bit more involved to really challenge you, and there's nothing wrong with that. And even more advanced problems and using concepts from other chapters to get through there. Then I see here answers to the section exercises, answers to the practice exercises, and then on to the next chapter. So have fun with all of this. It's good stuff.